Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's geometry lesson, we will be learning about proportional perimeters and areas in triangles. Let's get started with the following problem. A triangular shaped souvenir in figure 1 with sides 4, 5 and 8 is similar to a triangular landmark in Perth, Australia as shown in figure 2. If one of the sides of the triangle in Australia measures 10, compute its perimeter. So how do we solve this problem? It seems like that we don't know which ones has side length of 10 for the triangle in Australia. And also in figure 1, we don't know which side has length 4, 5, and 8. So let's ask ourselves, how many possible answers could we get here? Well, if we use 4, 5, and 8 respectively for one of the sides for the triangle in figure 1, then we can actually obtain 3 different answers. So let's try it. So let's look at the first case. Let's assume that the triangle in figure 1 has sides 4, 5, and 8 as shown in that order. And in figure 2, let's fix one of the sides to be 10. Which is the bottom one. So how do we find the perimeter of this triangle in figure 2? Well, it is given in the problem that these two triangles are similar. So we can designate the triangle from Australia to have sides x and y as shown in the figure 2. And again, since the two triangles are similar, we know that there has to be some type of proportion. Because we know that from the postulate that corresponding parts of similar triangles are proportional. Now we can set up a proportion here. We can say that 8 over 10 is equal to 4 over x. So if we solve for x, we obtain x is equal to 5. Similarly, we can say that 8 over 10 is equal to 5 over y. And that is going to give us a y value of equal to 6.25. Now our goal is to find the perimeter here. So if we add up all the values of 10, 5, and 6.25, we end up with a perimeter of equal to 21.25. Okay, so at this point, it would be interesting to compare the perimeter of the triangle in figure 2 with the perimeter of the triangle in figure 1. So what is the perimeter in the triangle of figure 1? So the perimeter of the triangle in figure 1 is simply 17, okay? So now we have both of these perimeters. How do these perimeters compare? So if we compare the first perimeter of 17 over the second perimeter of 21.25, and if we simplify that, we end up with 68 over 85. And if we multiply the numerator and denominator by 4, and we're doing that to get rid of the decimal in the denominator, we end up with a fraction of 68 over 85. And that can be simplified to 4 over 5. So does this number look familiar? So we know that the ratio of the first perimeter to the second perimeter is 4 over 5. What else is the ratio of 4 over 5? So let's compare the ratios of all the sides. For example, the bottom side, if we do the ratio, that's 8 over 10. What does that simplify to? Well, that also simplifies to 4 over 5. Now what about the left side? Well, the left side is simply 4 over x, and we did find the x value to be 5. So that simplifies to 4 over 5 as well. The right side has a ratio of 5 over y, and we figure out the y value to be 6.25. So we can write that as 5 over 6.25, which simplifies to 4 over 5 as well. Now notice that the ratio of the perimeters of both triangles is 4 over 5, and the ratios of the respective sides or the corresponding sides of these two similar triangles is also 4 over 5. So what do we learn from this? Well, we learn that the ratio of the perimeters of any two similar triangles is equal to the ratio of the sides. But we know what the ratio of the side is called, right? And that is called the scale factor. So again, the scale factor is the ratio of the lengths of the corresponding sides of the polygon. That is also called the ratio of similitude. So the pertaining theorem now is if two triangles or polygons are similar, then the ratio of the perimeter of the triangles is equal to the scale factor. So now that we know this information, how can we use this theorem to figure out the other two cases pertaining to the triangles? Let's now look at the second case. How do we use the theorem that we just introduced to figure out the perimeter of the second triangle, or the triangle in figure number 2? Given that the sides in figure 1 are swapped now. Now we have that on the left side, that's side length of 8, the right side is 4, and the bottom side is 5. Well, let's figure it out. What is the scale factor? So that's the first thing we need to find. So the scale factor is simply 10 over 5, which is equal to 2. So that means that if we compare the bottom sides of 5 and 10, we can say now that the triangle in figure 2 is double in size than the triangle in figure 1. So what does that mean in terms of perimeters? Well, we know that the perimeter in the triangle in figure 1 is 17. We also know that the ratio of the perimeters of both triangles is equal to 2. We also know that the ratios of the perimeters of both triangles P2 over P1 is equal to 2. Then we simply substitute 17 for P1, which means that the perimeter of the triangle in figure 2 is simply 34. It's also double in size in terms of the perimeter. So as we can see, using this theorem simplifies many calculations here. So let's look at our third case now. So for the third case, let's assume that the triangle in figure 1 has the following sizes as shown in the figure. So in this case, we want to again find the scale factor and then perimeter. Here in this case, we want to apply the theorem again, figure out the scale factor, and we can see that the scale factor in this case is 2.5, which means that the triangle in figure 2 is 2.5 bigger than the triangle in figure 1. Again, we know the perimeter in triangle figure 1 is 17. So we multiply 17 by 2.5, and therefore the perimeter of the triangle in figure 2 must be 42.5. So in this case, we just analyzed the scale factors, how they're related to the perimeters. How about the areas of the triangles? So let's look at that now. Now, for this particular problem, we first want to find the perimeters of these two right triangles, then find the areas of both of these triangles and compare the ratios. And think about, okay, how are the ratios of the perimeters related to the ratios of the areas? So let's look at this. So the perimeters are 12 for the first triangle on the left and 36 for the second triangle on the right. And this makes sense because the scale factor is equal to 3. So therefore, the perimeter in the second triangle is 3 times larger or 3 times bigger than the perimeter of the first triangle. What about the area? So if we calculate the areas, we obtain an area of 6 for the first triangle and the area of the second triangle is 54. So how do these ratios compare? If we take the ratios of, let's say, area number 2 over area number 1, we get 54 over 6, which simplifies to 9. Now, if we compare that to the scale factor, we can see that the scale factor is 3, which is also the ratio of the perimeters, and the ratio of the areas is 9. So it turns out that the ratio of the areas, since we're talking about square units, the ratio of the area is equal to the scale factor squared. Okay, so now that we have investigated this, we can now introduce the theorem pertaining to the ratios of the area. So the theorem states the following. If two triangles or polygons are similar, then the ratio of their areas is the square of the scale factor. Okay, so now that we have introduced two theorems, one pertaining to the ratios of the perimeter and the scale factor, and one of the theorem pertaining to the ratios of the areas and the scale factor, let's introduce one more theorem or one more concept in geometry that has to do with triangle proportionalities. Let's look at an example now. Let's say we're given that segment DE is parallel to segment BC in this triangle ABC. And we also know that AD is equal to 5, BD is equal to 2, EC is equal to 1. Then what is the length of segment AE? In this case, we denoted segment AE as X. So in this particular example, we want to see if there are any triangles that are similar. And indeed, they are. Here we know that angle A is congruent to itself by the reflexive property. Then we also know that angle ADE is congruent to angle ABC, because if two parallel lines are cut by a transversal, then corresponding angles are congruent. Therefore, triangle ABC must be similar to triangle ADE by the AA similarity postulate. Now, since the two triangles are similar, we can now express a proportion. Basically, that 5 over 7, 7 being 5 plus 2, and that is equal to x over x plus 1, because by corresponding parts of similar triangles are proportional. So all we need to do here is cross multiply to obtain 5 times quantity x plus 1 equals to 7x. Well, we know that is true because the product of the means is equal to the product of the extremes. And then we simply solve for x. So here we obtain an x value of equal to 2.5. Now, if we look at the value 2.5, we can actually figure that out in a different way. If we look at the segment AD and segment BD, we know that those are 5 and 2 respectively. So it turns out that we can also do the following proportion here. We can also say that 5 over 2 is equal to x over 1. So we're basically taking the proportions not based off the entire triangle ABC and ADE, but just parts of it. So we're saying that 5 over that little piece BD of 2 is equal to x over that small piece of 1. And that is actually going to give us the same answer, namely that x is equal to 2.5. Now, is this always true? Well, let's test that out. Let's say we're given triangle ABC, and we're also given that segment DE is parallel to segment BC. How do we prove that AD over BD is equal to AE over CE? Well, as in the previous problem, we first need to look at the triangles that are similar here. We can say that angle A is congruent to itself by the reflexive property. Then we can state that angle ADE is congruent to angle ABC, because if two parallel lines are cut by transversal, then corresponding angles are congruent. Therefore, triangle ABC must be similar to triangle ADE by the AA similarity postulate. Now we can set up a proportion. We can say that AD over AB equals to AE over AC by corresponding parts of similar triangles are proportional. Since AB equals to AD plus BD and AC is equal to AE plus CE, we can now substitute and rewrite the proportion as AD over AD plus BD is equal to AE plus CE. So what we can do here is cross multiply and divide, or we can just simply flip the proportion around and say that AD plus BD over AD is equal to AE plus CE over AE. Why are we doing this? Because now we can split the fraction. Now, splitting the fraction, we get that AD over AD plus BD over AD is equal to AE over AE plus CE over AE. Now, what is AD over AD and AE over AE? Well, we know that's just simply 1. So at this point, we can just simply cancel the 1 or subtract 1 on both sides of the equation to obtain that BD over AD is equal to CE over AE. And all we need to do now is flip that proportion again by cross-multiplying both sides and dividing, and we obtain that AD over BD is equal to AE over CE. And that is basically the proof. Now that we have proven this, we know that this is actually always going to be true. And therefore, this becomes a theorem. So the theorem states that a line segment joining two sides of a triangle is parallel to the third side if and only if it divides those two sides proportionally. Okay, so that's basically it for today's lesson. I hope you enjoyed it. Thank you for watching and have a wonderful day.